Well, Henry's built a very strong argument that brings up Dr. Shee's work and is going to convince everybody that we need Dr. Shee's results and to implement what he's going to show us. Dr. Shee is currently an associate professor in civil and environmental engineering at Washington State University. He has more than 20 years' experience conducting engineering and science research with a demonstrated publication record. During 2004 to 14, Dr. Shee was laboratory director and program manager at the Western Transportation Institute. He holds a PhD in chemistry, among other degrees. Dr. Shee.
Thank you, John, and good morning, ladies and gentlemen. And I feel like after a long TRB week, it's a little bit daunting. But yeah, Henry did a wonderful job laying the foundation, like why we need this type of research. And this study was funded by Clear Roads program, which was a pooled fund study when I was still program manager at Western Transportation Institute. So now I'm with Washington State, and my collaborators are Maddie, who's my postdoc, and then my collaborator Dave is in the private sector, and Laura Fay. So the study is really looking into developing a manual for equipment engineers or managers to see how to deal with this very issue, best practices. It's kind of building on a previous study we did for Washington State DOT, where we did some literature review looking into the best practices in the published domain, and also a almost international survey of what industry is doing to mitigate this concern, especially how big is the problem and what the key issues are. And then we identify some best practices, especially best products. The best is really quote unquote, because it's really from the industry what they feel was the best, say coating, anti-corrosion coating, or corrosion inhibitor, or salt remover. So we tested them in the lab. Again, it's a short-term test. Unfortunately, so far I haven't been able to convince any agency to fund a real study, look at in the field how they perform. So whatever we came up with in this list is mostly building on, again, the previous WashDOT study and a few other studies, and then some lab results. So they're not necessarily the final say on this issue. So with that, today I'll talk about a little introduction and go over corrosion science 101 a little bit. The definition of corrosion, causes and effects, and then look into best practices in terms of materials. First, also a little bit of context, like what type of materials are used in silicon ice control and why corrosion is becoming a significant issue, and then look into best practices to mitigate such issues, like starting from the equipment specification stage to a later stage where you're dealing with repair, rehabilitation, and then also talk about PM, preventive maintenance practices. I think Henry hinted on that a little bit, and also training and facility management, because no matter how best the practice is or are, people are the ones implementing the practices. And then we'll conclude with some discussion. Now, first, to kind of establish the context, in the last 1 or 2 decades, because of the higher demand for better level of service and for a number of other reasons, including environmental concerns associated with abrasives, then agencies start using more and more de-icers. Now, these de-icers mainly for roadways, they mainly contain chloride-based salts for freezing point depression, because they cannot afford those magic de-icers they use on airports where they're much, much more expensive. They're non-chlorides. So these salts certainly are becoming a concern over the years. Here, this talk will focus on the risk to DOT equipment in terms of value depreciation, the safety concern potentially, among other things. But actually, there are more issues to it. For instance, there's the impact on natural environment, the risk to concrete pavements, and even asphalt pavements, and also to bridges. So the list goes on and on. But again, winter maintenance, why we do it? Because there's significant safety and mobility benefits. So we have to do winter maintenance. We cannot go back to the old days with very little maintenance. So we're looking at this sad effect of doing winter maintenance, which is corrosion to equipment. Now, studying a little bit definition of corrosion, basic corrosion is defined as a material's deterioration due to reaction with its environment. Typically, we're not talking about the chemical reaction. We're talking about so-called electrochemical reaction. So I'll show that in the next slide also. Basically, there are multiple types of metals used in cars. And back in the 60s, back in 50s or 60s, when road agencies started using more rock salt or salt brine, back then the cars were corroding really fast. So the manufacturing industry managed to design better cars to mitigate that issue. And in recent years, because of the new chemicals, it seems like some of those designs or coatings or materials didn't work as well. So again, it's a host of materials used in our vehicles and equipment. So, and the corrosion is quite complex, as I will show in the next few slides. It could take multiple forms, and it could be highly localized and nearly impossible to prevent or design for prevention. Because the analogy I use is for bridge engineers. Often we think in terms of safety factor. What if I just design thicker, so maybe the problem will go away because I have a safety factor? As you will see very soon, that doesn't work. I know this is probably back to high school chemistry or college chemistry, but basically corrosion takes place through a way. Well, very simple example is iron. Actually, in steel, it's mostly iron and a few other things. But when iron corrodes, what happens really, you take two half reactions to make it happen. One is iron would oxidize and produce the electrons. And those electrons need to be consumed by somebody. So it's a give and take relationship. You need also the oxygen and water to consume the electrons produced by the iron oxidation so that that reaction will continue. So with this science, basically what you can do in terms of corrosion management is you try to suppress or prevent one of the half reactions. For instance, if you don't have any oxygen or don't have any moisture, then corrosion will stop because the electrons have nobody to marry with, basically. Now, corrosion can take many forms. One type is general corrosion, or also known as uniform corrosion. Well, that rarely happens in our real world, unfortunately, because usually if it's a uniform corrosion, it's really easy to prevent because how fast it's corroding, say 0.1 millimeter per year, then you can simply design it thicker or something like that, or use a better material. The thing is, sometimes, as I'll talk later, there are many types of, I would say 99% of the time it's localized. That becomes really difficult. Again, some of the practices to deal with general corrosion or uniform corrosion, really using better or more corrosion resistant material, using coatings, using corrosion inhibitors. Now, there are many types of anti-corrosion coatings, many types of corrosion inhibitors. Much of the trade secrets is really not known, right? But there are certain science to it. Basically is, again, trying to choke one or both of the half reaction. Either you prevent iron from oxidation or you prevent availability of oxygen or moisture. So now, when it comes to localized corrosion, like I said, in the real world, especially when we're dealing with equipment corrosion, that's the main thing we're dealing with. Unfortunately, they're typically highly localized in confined areas and cause unexpected failure. So it's pretty hard to predict when they will fail. So basically, for safety reasons, for performance reasons, we have to check them very often. So that increases the cost in terms of inspection and whatnot and maintenance. Now, there are many types of localized corrosion, and pretty much all of them could occur on the vehicle. So it makes it really a daunting task to manage the corrosion. I'll just give some examples. For instance, pitting is very common. Basically, you see a hole, it's pitting. And also crevice corrosion. When you have crevice, you have some area you're accumulating the risk of corrosion. And another form is undercoating. You could have so-called field form corrosion. And for certain types of metal, like stainless steel and aluminum alloy, you could have another type of corrosion. It's called intergranular corrosion. Basically, corrosion initiates along the, well, this is really microstructure level, along the, granular grains and starts to propagate. So it starts cracking and, propagation of cracks. Galvanic corrosion, that's one I think not only equipment engineers, but also bridge engineers often forgot, is when you try to design something, you think more about stress strain, mechanical properties. So you hook them together, say with aluminum versus a stainless steel, a carbon steel versus stainless steel. Maybe they work beautifully, look nice, but what happens, you are initiating a battery, basically. One is sacrificing itself to protect the other. So you look at these screws, basically, okay, one is corroding really fast to protect the other. So it's highly localized and it's nearly impossible to predict. And then another type is called stress corrosion cracking. So when you have tensile stress applied to that frame or whatnot, Henry was talking about the frame cracking. Now, with tensile stress coupled with corrosion, the electrochemical attack, I was talking about the electrons, transfer, the two together can make things much worse. Now, another type is corrosion fatigue. When something is under constant cyclic loading, mechanical loading, and then you have corrosion on top of that, you have so-called corrosion fatigue. Again, it's much worse than simple fatigue or simple corrosion. And then, this is one type of, rust jacking is one type of corrosion fatigue. And also in some cases, again, you have some threading corrosion because two pieces of metal is constantly, annoying each other mechanically. And on top of that, especially when we're using sugar beet or some organic materials as de-icer, we run into this risk even more, which is microbially influenced corrosion. Bugs love sugar. Well, of course, in some cases, the desugared molasses is a different story because they no longer contain sugar in them. But at least they still contain higher contents of carbon and nitrogen, and that when the stormwater runoff containing this de-icer gets into adjacent waterways, that's a concern for water quality. But when they're sticking on the vehicle, well, a lot of times these organic de-icers are designed to stick to the roadway longer, so they are sticky by design. But now they're sticking to a truck and it's harder to wash off. Actually, unintended consequence, you may have more corrosion potentially. Now again, localized corrosion is very dangerous, we already mentioned, because remember the two half reactions. One is trying to oxidize, create a lot of electrons, and those electrons need to be consumed by somebody else. So when you have localized corrosion, what happens is, especially when you, say for instance, one example is you have a coating which is dented, you have a hole. That hole is becoming so-called local anode. It's trying to produce a lot of electrons to protect adjacent areas because it's a marriage. Now, this is not equal marriage. So all of a sudden, that hole is corroding 10 times faster than it would be in terms of the uniform corrosion rate. Well, 10 is just an order of magnitude, but it's highly difficult to predict how fast it's exactly corroding. That's the same issue with chloride-induced rebar corrosion. There's no way you can simply design rebar to be thicker and avoid that problem. You still have that problem because that area corrodes really fast, and then it could have structural failure or whatever consequences. So when it comes to pitting corrosion or undercoating corrosion or under-deposit corrosion, another issue is you have areas where oxygen is having a difficult time to get in, and somehow the local chemical environment has changed. The pH drops, so that local environment becomes really acidic. That becomes an issue. Now, in the case of organics, organic de-icers, very similarly, the metabolism of bugs, microorganisms, could be very acidic. So that adds to, chloride is already bad for the metal. Now, on top of that, you add acid, that's even worse. So basically, again, the reason we use chloride is because they're cheap, they're easily available, they're easy to handle, and everything else, it's great for winter maintenance. But you got this corrosion problem, and according to the survey we conducted in the Washington study, basically the respondents were mostly northern states. Typically the majority of them were northern state DOTs. A few of them were cities. But on average, we're talking about right now how much they're spending on corrosion management. Now, keep in mind, this is just corrosion management. We're not talking about the the direct or indirect cause of corrosion-induced failure or repairs. This is just the no corrosion problem. We have to spend some money to reduce this issue. So this training involved this material selection. So many of these, well, is related to, will induce some cost. But if this corrosion-induced repair or replacement or failure, especially failure on the road, that's a different story. That's even worse. So with that, we also surveyed which are the corrosion-prone parts on your trucks or vehicles. The most severe turns out to be electrical wiring at the top because, again, we talk about electron transport during corrosion. Now, if you're running a current through that wire, that's on top of that other electron transport, so make things really worse. And also frames, well, Henry was talking about frame cracking, it is a big deal because it's structural failure. And brackets and supports and among other things. Now, certain things are really expensive to repair or replace, like the chassis, like the axles, the brakes. Well, when you see brakes, you get really alerted because trucking associations have been complaining for years that somehow, well, maybe it's anecdotal, in some cases, because of the wiring failed and the brakes didn't work and they ran into safety concerns. Now, the survey also looked at what type of metals or materials are used in vehicles, equipment exposed to winter operations. And again, as you can see, we talked about earlier, all types of materials like cast iron, but different metals have different forms of corrosion. Usually the equipment engineer is not necessarily knowledgeable about corrosion science. Just by visual, you can see, okay, it's uniform versus localized corrosion. But again, like we said, localized corrosion could take many different forms by many different mechanisms. Now, so in this case, we thought, well, it may be necessary to run some sort of cost-benefit analysis to examine this issue. Unfortunately, like Henry was talking earlier, such data are not available. Oftentimes, the repair cost is not segregated such that you can identify which costs are due to de-icer corrosion, for instance. So we had to rely on some assumptions. Even in that case, we say, well, if we use the 20-80 rule, if we think 80% of the corrosion, well, before I even go there, the corrosion actually is a natural process, just like water falling down from mountains. So there's only 25% of it theoretically could be prevented. 75% of it, there's no way you can fix it. No matter how much money you invest in it, it's corrosion. So we're targeting that 25%. If we can do away with 80% of that 25% cost, okay, let's see how much we can save. So we're look at, okay, let's identify those critical 20% of the corrosion failures and focus on training, risk-based maintenance, and so on. Then we came up with some number using the average. Again, it's really biased by whoever responded. So we had, I think, 40 some responding agencies. In those cases, basically, we used this assumption and we got 13.2. That means you invest $1 million, you're saving $13.2 million down the road in terms of de-icer corrosion to your equipment. But again, the real data is not available at this moment, so we had to rely on survey responses, assumptions. That's where, it was a little bit shocking to see that, agencies are not documenting this issue. Now, going back to a little bit, materials used for snow and ice control, we sort of talked about many of them, but well, back in the old days, of course, sanding was the dominant way. And of course, on top of sanding, you have plowing. Basically, how it works nowadays, however, is you typically rely on really good weather forecast, and then you start so-called proactive maintenance. So you try to put down most typically liquid products, salt brine, magnesium chloride liquids, and so on, to prevent the bonding of the snow and ice to the pavement, so that it's proactive. And then if that failed, if the forecast was wrong, it was too cold and it refreeze, or for whatever reason, or you didn't get the forecast, now you already have compact snow keying into the pavement and the bond is really strong. What you do next is so-called de-icing. You typically apply solid products on top of the ice layer, and it will melt a little bit of ice and then penetrate through the layers and then undercut the the ice layer so that it's easier for mechanical removal. Again, the intention is not to melt the entire amount of snow and ice on the pavement. That would take 10, 20 times more than what DOTs are applying nowadays. So it's really just trying to get the chemical to work so that it can weaken the bond. Now, that's de-icing. And then, of course, de-icing, as I implied, you're still relying on mechanical removal. So you still couple de-icing typically after 45 minutes or so, then with plowing. And then if all three we mentioned, anti-icing, de-icing, plowing, all failed, well, now the ice is really thick, and there's no way you can afford that much material to, break down the ice. What you do is sanding. You are providing a temporary friction layer. So in those three, anti-icing, de-icing, and sanding. In sanding, because the dry sand can be easily blown away by traffic, so you need something to help it to stick to the ice layer. Usually, or in Europe, they use hot water in some cases, but in the US, we use liquid de-icers oftentimes. So in those three operations, we use some chemical. So those chemicals, chlorides. Sodium chloride is still the dominant because cheaper, or at least the purchase cost is cheaper. We're not necessarily looking at life cycle analysis or all that. For the moment, we're mostly relying on, okay, it's cheaper and it's readily available. And then there's calcium chloride, there's magnesium chloride, and again, airports use a lot of potassium acetate. They're much more expensive in terms of direct cost, but they are used for some key locations, like anti-icing system on bridge decks. And then calcium, magnesium acetate, and other things. Now, we already mentioned the agricultural byproducts. They work wonderfully because they stick to the road longer, and they seem to have some way to weaken that ice. We're talking about cutting the bond. Now, even if they freeze, that ice microstructure, and when you look under the microscope, they're different, they're weaker. So there are benefits, but in terms of corrosion, well, I actually did a presentation on Monday. It's kind of complicated, depending on how you wash it, whether or not you use salt remover. Yeah, it's a lot of things to it. Now, if we're starting from the beginning, of course, at the equipment specification stage, if we have this corrosion issue in mind, we would try to specify certain types of materials, especially we know certain components are highly prone to this de-icing corrosion issue. We would do it a little differently. In doing that, of course, you may bump up the cost 10, 20%, but it's worth it if you look at life cycle. In the state of Oregon, for instance, I know Bruce was still sitting there. One group of equipment was designed for 15 years, but only in reality lasts 10 years. So if you can extend that service life back to its original design life, the savings would be tremendous. Now, so if we specify them and design them to last, as much long as possible, then we typically can do a few things at this stage. For instance, we can do better job at material selection, better metals, design improvements. We'll go over a few of them because many of those are consistent with the science, corrosion science we're talking about. You prevent water accumulation, you prevent localized stress concentration or localized moisture concentration or whatnot. You can minimize or reduce this issue. Welds. There we, again, going back to stress concentration and other issues, coupled with corrosion. So usually they are the trouble areas. And then coatings for corrosion prevention or protection. Now, many of these items are from literature, from the industry where corrosion prevention is a big industry. What's interesting is there's a huge disconnect between academia and industry because in academia, there are very few programs nowadays teach corrosion science at all because it's not fancy. It's down to earth and it's not popular. But anyways, so in industry, there are a lot of engineers who learn how to select materials for the intended application, intended environment. One example, for instance, okay, in certain environments, we have a high risk of SCC, or so-called stress corrosion cracking, then we should select certain types of carbon steel. Now, we know also for even stainless steel, even though the name implies stainless, well, if you put them to test, certain environments can be very demanding, and they do stain, they do corrode, typically through pitting or intergranular corrosion and such. So, there are certain types of stainless steel, like 316 stainless steel, will last better or longer than other cheaper types of stainless steel. Again, it's all about the intended environment, intended application. You need to know, it's not like a one-size-fits-all. Now, in terms of design improvement, again, earlier the science says, well, if you can prevent water accessing the metal surface, then you do away with many of the corrosion problems. So drainage is important. And also, in terms of coating, okay, avoid sharp edges, because if, like we mentioned, if the coating is dented or somehow has a defect due to the sharp edge or due to the application process, then you got a highly localized corrosion going on. It goes much faster. And on top of that, if you have under deposit corrosion, you could have a highly localized pH drop. It's very acidic. Anyways, so it gets really bad to have those designs. And then stress concentration, like we mentioned, either in corrosion fatigue or in SCC, stress corrosion cracking, the stress, the mechanical stress is really accelerating the corrosion. So if we could relax the stress, that's better. Now welds, again, it's a big problem. So wherever basically you have localized features, which is stress concentration or whatnot, or dissimilar metals touching each other, you got a problem. So unfortunately, traditionally, many of the design are either focused on, mechanical properties or considerations, or targeting sodium chloride. But now with magnesium chloride, like I presented on Monday, it shows that the attack takes a little bit different form. So some of the designs, targeting the sodium chloride no longer work well in the new surface environment. Now, in the industry, it's very common practice to use zinc-rich coating. The reason is we have no confidence that without the zinc, the coating will do a good job. For instance, if that coating is dented, again, that area becomes a weak spot, and probably that case is not much better than without the coating. You got a localized corrosion going. It's a self-accelerating process. Now with the zinc, what it does is the zinc will sacrifice itself and pump some electrons to protect that hole, that dent. So it's very common practice nowadays. Now, in terms of the weld, well, there are many items we collect from literature, from the survey responses, but the bottom line is the welding process induces some heat-affected zones. In those zones, you got a problem. And by designing it differently, you can minimize the issue or the risk. Now, coating, like we mentioned, nowadays the coatings are getting really complicated. A lot of them were targeting, much more demanding environment than our environment, which is the equipment on the roadway. One thing I forgot to mention is corrosion actually goes relatively slow when it's cold. So it's really when it warms up, when your truck goes back into your garage, that's where it kicks in. And when it's out there in the field, actually, because corrosion is a chemical process, the temperature is having this effect on it. Or in another way to describe it, your electrons and all the other things are moving very slowly. Chlorides, whatnot, moving very slowly because they are lazy. They're kind of frozen. They don't move fast. Once you heat them up, all of a sudden they move really fast, and then your corrosion goes really fast. Well, that's the same issue with the bridge. So that's where I recommend DOTs to wash the bridges during spring, so that the residual salts is not there by summertime. By summer it's really, really kicking in the corrosion issue. Now, the coatings, certainly we have a lot of desires or multiple requirements for coatings. You want them to be easy to apply, they're environmentally friendly, they're long-lasting, and everything else. Ideally, they're also cost-effective, they are scratch-resistant, Coatings. But one thing often ignored is surface preparation. You cannot simply take a coating and put it on a dirty surface. And the challenge is how to remove the residual salt. That's where the magnesium chloride, calcium chloride behave different than sodium chloride. It's really hard to remove them from those crevices or hidden areas. So then you put on a coating, your coating won't last long. So salt removers are designed to do that. They have been demonstrated to do a very good job in terms of protecting bridges. When you wash bridges, before you put on protective coating, usually you incorporate some sort of salt remover. There are less studies, other than, I guess, our study, focusing on using salt removers to protect equipment. Now, I didn't want to get into the details of many practices you can do into the repair and rehabilitation, because I think the best approach is still try to be preventive, proactive, so that you don't have to deal with as much retrofitting or repair. Now, preventive maintenance, again, is very similar to pavement management or to bridge management. If you invest $1 million relatively early in the stage, you avoid $5 million cost down the road. So it's kind of intuitive. Certainly, sometimes it's too late. Like I said, the corrosion, you can prevent 25% of it, but there are cases, there's no way you can totally prevent, well, unless you invest tremendous amount of money, use ridiculously costly, materials. That's not the scenario we're dealing with. So when you're having some issues, you get involved. So, or salt remover or sandblasting, putting back a new protective coating and things of that nature. You could do that. Or like Henry was saying, the frames, you can try to reinforce it and it will last another 2 years. Those cases could be useful in some scenarios. We're not, saying reactive maintenance is not important or we should totally avoid that. But what we really should be focusing on is preventive methods, because there are so many of them, starting from the design stage, material selection stage. For instance, we can do a better job enclosing the wire connections so that they're not exposed to the water or the ices. So you do away with that high risk. Or we can use sacrificial anodes or sacrificial coatings to, again, sacrifice themselves to protect, the metallic substrate you're trying to protect. So again, it's basically galvanic corrosion in the other direction. It's using that phenomenon to help you. Certain coatings can work really well, and washing is important. Of course, like Henry was mentioning, DOTs are sometimes concerned about this wash water issue. How do we deal with that? And so there needs to be a more systematic analysis or approach to this problem. Wash the vehicles daily, that's the recommendation. Certainly that would generate some wastewater, and some DOTs are trying to recycle that wastewater and put it back to use in terms of making salt brine, for instance. Of course, every once in a while they need to be sampled and make sure there's not too much heavy metal or whatnot, so it's still good, meet the standard for de-icer specifications. So that's a good practice. Washing should focus on trouble areas. That's kind of intuitive. And one thing we learned from survey and also from our own lab testing is, usually after washing, you better dry it fast, because the corrosion really kicks in when it's the humid stage. Once the humidity dropped to, say, below 30%, corrosion stopped, basically. Okay. So pressure washing, it seems like pressure washing is not best practice. Need to do a different way. Use salt removers and so on. So sometimes once you wash it clean and put on protective coating, or sometimes you don't have protective coating, you can spray products called corrosion inhibitor. Basically what they do is form an oily layer in most cases to prevent oxygen accessing your metal. On Monday, the study basically I presented is salt removers are metal specific. They work for certain metals but doesn't work for other metals. So it's a little risky. And once you do pressure washing, you could wash away this protective organic layer. Well, there are also electrical issues. There are practices, you can do that. So I didn't want to go too much there. Well, don't probe your wires again, otherwise you dent and you got localized corrosion. And some grease can help you. Basically, you're preventing water and oxygen to access your metal. So many of these items are available. The reports on Clearwater's website. So I didn't want to go too much into that. In terms of chassis and brake, again, you could do protected coating, you can do spray-on corrosion inhibitors, make sure they're clean before you do that. And for other parts, the list basically is from the server responses. Now, training, again, like we mentioned, people at different levels in the organization need to be aware of this issue and be trained about best practices. So to conclude, first of all, agencies should be tracking this de-icer corrosion-related cost data. Otherwise, there's no way we can, if we don't measure, we cannot improve, basically. And also, we should implement extensive preventive maintenance so that we can save money down the road. And it could be further supported by reactive or corrective maintenance practices. And again, training. Thanks for your time. And I'd like to acknowledge the sponsors and technical panel, colleagues. I'd like to take any questions you may have. Thank you.